suggests now is that we have this very Bayes variational principle, right? So this suggests that if you have an additional structure, like that the X sequence or the X process is a Markov process or a Markov diffusion process, and you have structure in the observation, then you expect that that variational problem should have some stochastic control interpretation, i.e. dynamic programming. Okay, and that is indeed the case, and this makes a case for that. Not very good. Okay, so let's look at this equation, right? So what we come down to is the following, that you have the observation y, it's a path, it's a sequence or a path, and the state is x, right? So the idea is to think of the estimation problem as that there's available some additional control, if you like, and you would like to track the Y process as best as you can. And this is what this says, that the prediction without the observation would be some g of x of t, and you want to match this Y to the observations Y with some constraints of the amount of energy, control energy, that you want to put. Now, this stochastic control problem has a dynamic programming. And if you look at the recent neural network literature and etc., there are certain equations that arise there. For example, Berger's equation are exactly dynamic programming equations. Okay, this is what I've said. This involves an energy term for the control and the least squares term for the observation path fit. So these corresponding to the two terms of the relative entropy term and the average likelihood term. Now, it's not unsurprising that the optimal control turns out to be a gradient of the value function. So the ideas that I'm discussing now are intimately connected to issues of, for example, sampling from Gibbs distribution and gradient flow on the space of probability measure. There's a whole series of things. And also this exploits the fact there's a close connection between dynamic programming or Hamilton-Jacobi equations and sort of parabolic equations via transformation of Black's transformation. Okay. Now, the remaining question that I want to ask is more or less written down here. So that's the observation equation. We get some nonlinear function of some state process just as white noise. And Z of t is we said the fundamental object is the conditional distribution. You have to understand this map from the observation to the conditional distribution. Okay. Now, here, because of the Markov structure, we can write down what the evolution of the conditional distribution, or more precisely the conditional distribution is. So this part of this evolution, this is the Fokker-Planck equation, right? That's the equation which tells you how the probability density of the Markov diffusion process evolves in time. And this is a correction term which involves the so-called innovation process, which is sort of adds in the right way the information that you get from the observation. Now, the question that we wish to ask is, in information terms. So, for example, we want to write down the information flow from the observations itself to the conditional distribution, right? So so we want to identify things like the supply of information, the information that's stored by the filter itself, namely this density psi t of the observation, and the flow of the dissipation. So I think it's quite beautiful because it says is that the optimal filter stores the minimal amount of information that it needs in order to make sense of the present and the future. And it dissipates the information that is not needed as the information is being transferred from the initial state and perhaps the input into the observation, and throws away historical information at an optimal rate. And the optimal rate is given by the Fisher information. So one has a precise relationship between the Fisher information, which, by the way, is related to problems of identifiability as providing a Riemannian metric, and throws away historical information. And the point is that this is all written down in terms of mutual information, which is an invariant quantity, invariant under diffeomorphism. And more or less, I can stop here. That the implications of this viewpoint, I think, is a neural network. When you look at minimization of functions, or even perhaps non-convex functions, and how you're going to interpret training, etc., and how would you analyze convergence of things like stochastic gradient. So that's what I have to say. Well, the idea would be that the natural notion of distance is now this pseudo distance given by the mutual information, and at each step you'll you take a variational view of principal component analysis, and each step you'll solve a variational problem, right, which involves minimum distance from starting procedure. Now, what I have not, at the moment, I'm not able to make, in what sense is this more informative to take a classification problem. I'm saying this metric, the choice of this metric it's task dependent. I mean, maybe there is some universal sufficient statistic, but I'm not sure about that. I mean, that could be roughly the idea. Yeah. I mean, you'll have to, for example, learning will come into the picture and in understanding the prior information somehow. And that's this teacher-student interaction that Daphne is talking about. So one thing is, how would you do this Bayesian inference when you have group action, right? There are many problems there we have to really keep the symmetries. You have to be faithful to the symmetries. So you have to build in invariance into these variational principles. I don't have a general answer, but I'm saying that could be the main pillar around which you understand problems. I really couldn't understand the question. If the XC process is singular, sorry, what is singular? Ah, diffusion coefficient. Well, I mean here I'm assuming. So in the proof that we give, we do not require uniform ellipticity or the stochastic differential equations can be quite general. If you look at our paper, the theory would still go through. I mean, all you need is some weak solution to these stochastic processes. I don't know if I've answered your question. An interesting problem, of course, is if the X process is the noise goes to zero, that's the difficulty.